Good afternoon, everyone. I'm Dr. Thomas Heverin, and again, I'm presenting with Caroline Ma and Avery Warrior. We hail from the Baldwin School, an all-girls private school out in Bryn Mawr, Pennsylvania. And our talk is entitled LLM SRO, Ontology-Driven Security for Large Language Models. So thank you for attending our talk. So first, I'd like to share a bit of our background. I think I could spend the whole presentation bragging about what these two researchers have done, but also other students. So in the picture depicts my AI and cybersecurity class. So at the Baldwin School, I teach ethical hacking 1 and 2, and I also teach AI. And I make the classes hands-on to feel like, so the girls can feel like they're making a real impact live in the classroom. This picture is from a field trip to the FBI Computer Forensics Lab in Radford. But some of our ethical hacking achievements in our classes. So we reported on hundreds of vulnerabilities, including IoT devices, printers, security cameras, classroom display systems. We showed in and mapped various tools, and we even created our own hacking tools based on Python, such as tools that can hack into FTP, into telnet servers, IoT devices, and many more types of devices. We also have authored an exploit DB entry. Exploit DB is an exploit database full of different exploits that can be used against different products. So we created an exploit DB entry on Solstice pods, which are classroom display systems. We found that we can grab the live session key and then get into the display systems and display whatever we wanted to, ethically, of course. And we also developed partnerships with UPenn, Drexel, and Villanova, and we've done some hacking projects with some universities across the pond in UK and also the University of Mexico. And I'd like to highlight some of our AI security achievements. So this group that we're presenting today, we have published a prompt injection research paper at a cyber warfare conference and also on arXiv. arXiv is an open, technical, scientific paper repository. We did a research study where we tried to exploit 36 LLMs with different prompt injections that we came up with. And a prompt injection is a way to trick an AI tool to produce content it's not supposed to, such as keylogger code or phishing email. We tested 36 LLMs and found that over half of them were vulnerable to our prompt injections. We also presented to MITRE, which is a federal contractor. We showed MITRE how we can use prompt injections to actually create some small-scale and large-scale industrial virtual system hacking modules. And we presented over a lunch and learn session. Over 130 cybersecurity researchers and engineers were there, and they stayed the whole talk. It was really cool. And my background, specifically, I have a PhD from Drexel. After I got my PhD, I worked down at the Philadelphia Navy Yard doing research, and which led to a patent focused on cybersecurity risk assessments on Navy ship systems, including like smart carriers. And in that work, we used ontology modeling and some algorithms to do risk analysis over Navy ship systems, which is relevant to our work that we're going to discuss today. So again, I think I could spend the whole session bragging about our accomplishments, or these two research accomplishments. But now I'd like to give you an overview of our technical talk. So first, I'll lead off with talking about the challenges of managing LLM risk. Because in addition to teaching ethical hacking in AI at the Baldwin School, I'm also the head of technology and cybersecurity there. We'll talk about the development of the security risk ontology. Avery will take over that talk. Creation of the SRO GPT, analysis that we can run with the SRO GPT and insights gained. Caroline will talk about these. We'll wrap up with some future research. So now, I'd like to talk from the leadership view about how hard it can be to manage LLM risk at an organization. And our talk focuses on the K-12 domain. So in terms of confidentiality, integrity, and availability, in managing risk, we're really focused on confidentiality. We don't want student information to be out there in the public. We don't want financial aid information about families out there in the public, health information about students, and many other types of data. But it's really challenging when teachers and staff start spinning up or start logging in using different LLMs, and who knows what they're uploading to those LLMs. So it can be hard to maintain awareness of how LLMs are being used by faculty and staff. Imagine them uploading grades or the learning profiles if students have learning differences. Imagine they're uploading that to a LLM and hackers get in and expose that data. It's really sensitive and private data. And then who knows what's happening with data governance and uncertainty in terms of FERPA, COPA, and others. So in the K-12 domain, we have certain safeguards or frameworks we have to follow. When I was serving in the Navy or working for the Navy research, there's different frameworks we have to follow there for guidelines. And unvetted integrations is a big concern too, because we don't know if a teacher or staff member is connecting one of the LLMs to our Google Drive. Who knows what the LLM is pulling? who knows how that data that teachers have now integrated is being used to train the LLMs. So it leads me, if I'm trying to manage the risk at the Baldwin School or another K-12 school, it can be really hard in terms of, it's really hard to determine like, where are the greatest risks at my organization in terms of confidentiality. All the different LLMs being used, different risk among each LLM, not sure what data teachers or staff are uploading to LLMs. It's really hard for me to determine by myself like where is the greatest risk. It requires a lot of manual analysis and a lot of work. Also, what are the best mitigations to use against those risks? So many of you work at organizations where you wish you had more cybersecurity IT staff. At the Baldwin School, there's only 3 of us maintaining IT and security for hundreds of staff members and hundreds of thousands of students. It's really hard. So doing that type of analysis, trying to identify where is my greatest risk is super challenging. So what can help answer those hard questions? An ontology model integrated with a GPT that provides easy access to complex analysis. So that's the basis of our talk. So the basis of our talk is we're going to talk about ontologies, like what they are, how they can be used, and then what we can do with an ontology once we embed that ontology into a GPT. And again, this work, the source of this work in my background comes from, again, the Navy research that I did resulted in a patent that focused on modeling Navy ship systems, all the software and hardware on the systems, how the systems are interconnected, and then using algorithms to calculate the risk over that model. So we apply that approach to the K-12 domain using ontologies and GPT. So now I'm going to pass it on to Avery Moore, who's going to talk about ontologies. Oh, wait, actually, pause on that. I'm going to keep going, because as a leader, I'm so excited to pass it on to my fellow researchers. Like, I can't wait. So I'm going to try to make this quick. So as a leader, when I'm trying to evaluate risk across my system, which is the K-12 system, there's some frameworks out there that I can use. For first off, of course, I want to know what LLMs are in use and what the functions are of those LLMs, or how they're being used. Then I want to know, well, what are risks out there? So yeah, I can come up with my own list of risks, but OWASP is the Open Web Application Security Project. Experts around the world, they determine together, like, what are the top risks against LLMs? So the top risk they determine is prompt injections, which are, again, ways to trick AI tools in producing content they're not supposed to. So they come with things that I can use to try to analyze risk in my system or mitigate the risk. These come with mitigations too. But I can also use Atlas, which is MITRE's adversarial threat landscape for artificial intelligence systems. It's a framework showing you how a hacker or someone on the offensive side is trying to exploit risk against LLMs. So they talk about Atlas techniques, which are specific techniques hackers will use to try to exploit risk on LLMs. They also provide mitigations and tactics. So we know in cybersecurity, it's really hard when we have to do like manual work and start from the ground up. I imagine someone already did some work for us. That's why I use frameworks in analyzing risk. And also, of course, we have the CIA triad, confidentiality, integrity, and availability. In a K-12 domain, we really focus on confidentiality, keeping the student data confidential, health data, learning profiles, learning differences, all that data, financial aid data, keeping that all private. So just briefly about OWASP top 10 LLM risk. You see the number 1 risk is prompt injections, and there's sensitive information disclosure, and a whole bunch more. So as a leader of cybersecurity and IT, I'm trying to analyze the risk of my systems. I'm looking at OWASP to learn more about specific risk I want to get more knowledge about. And within each risk, it's great because OWASP also says preventions and mitigation strategies. So if I'm not sure like what I can do to mitigate prompt injections, I can look at OWASP and get some ideas of what I can try or what I can do, or what's applicable to me. And what's really great too is that within OWASP also points to MITRE ATLAS. It points to the offensive techniques that one would use to exploit the weaknesses on my LLMs. So hop over to MITRE ATLAS, and they talk about direct prompt injections, and it also points to mitigations such as AI telemetry logging, and down at the bottom points to tactics, which are like the main strategies of attackers and execution. But MITRE ATLAS is a lot. So it's got many different tactics up top, which are kind of the main strategies of hackers, and it has different techniques that hackers would use. That's a lot for us humans to consume. I can sit there for months trying to understand this and analyze it and applying it to my school or any organization, or like to a Navy ship or a government system. So a lot of information to process, that's a data overload. And that's what leads us to trying to model this. Now, I'm going to pass it off to Heverin.
Hello. So an ontology, an ontology is a formal model of a domain that defines the key concepts, such as LLM products, risks, and mitigations, and the relationships among those concepts. In the context of LLM security, this structure lets us move beyond ad hoc lists and instead represent a unified map of what systems exist, what they do, what can go wrong, and how those risks can be addressed. Once this model is in place, it becomes possible to pose and answer complex questions over the entire landscape of LLM usage. For example, the ontology can support queries such as which mitigation strategies best reduce confidentiality risks across all deployed LLMs with the least implementation effort. That kind of question is extremely hard to answer reliably with spreadsheets or scattered documentation, but it becomes tractable when the concepts and relationships are formally encoded. The ontology is built from four main component types that together form a semantic network. Classes represent categories of objects, such as LLM product or LLM function, which organize entities into meaningful types. Objects are such as an individual product, like WiseNet AI, or a concrete function, like video surveillance. Data properties capture attributes of objects, such as an LLM function confidentiality impact score of 10, which invariably encodes how severely a function affects confidentiality if compromised. Object properties then link two objects together, such as WiseNet AI provides video surveillance, explicitly stating how products, functions, risks, and mitigations are connected. Now, by combining classes, objects, data properties, and object properties, the ontology becomes a knowledge graph that can be queried for patterns, dependencies, and optimal mitigation paths across many different LLM deployments. This slide introduces the core SRO classes and the object properties that connect them. The key classes are LLM product, function, LLM security risk, LLM security risk mitigation, Atlas technique, Atlas tactic, and Atlas mitigation. The arrows on the slide show how these classes relate to one another. Provides links an LLM product to a function. Impacts links a function to an LLM security risk. Exploits links an Atlas technique to an LLM security risk. Achieves links an Atlas technique to an Atlas tactic. And lastly, mitigates links an Atlas mitigation to an Atlas technique. And also can link an LLM security risk mitigation to an LLM security risk. Following these arrows from left to right shows an attack defense chain. Products provide functions. Those functions are impacted by risks. Adversarial techniques exploit those risks to achieve tactics, and mitigations push back on the techniques. Now, the abstract structure is grounded in a concrete example, so the arrow's meaning is clear. Here on the slide, we start with the LLM product Financial Edge NXT AI. The arrow label provides points from this product to the function financial aid tracking, meaning this LLM is used to support financial aid tracking tasks. The function financial aid tracking has an arrow labeled impacts, pointing to LLM security risk prompt injection. This indicates that this function is exposed to prompt injection risk. If the function is compromised, attackers can manipulate instructions given to the model to alter its behavior. The Atlas technique, direct prompt injection, has an arrow labeled exploits pointing to the same prompt injection risk. This shows that an attacker can carry out a direct prompt injection technique, specifically to exploit the prompt injection risk in the financial aid context. The Atlas technique, direct prompt injection, then has an arrow labeled achieves, pointing to the Atlas tactic, malicious execution. This models the attacker's goal. By exploiting prompt injection, the attacker achieves malicious execution, such as triggering harmful or unauthorized actions through the LLM. Finally, two mitigations appear. The LLM security risk mitigation human oversight has a mitigates arrow, pointing to the prompt injection risk. The Atlas mitigation AI telemetry logging has a mitigates arrow pointing back to the Atlas technique direct prompt injection. In order of the arrows, the example demonstrates the process. A specific LLM product provides a financial function. That function is vulnerable to prompt injection risk. A direct prompt injection technique exploits that risk to then achieve malicious execution, and targeted mitigations push back both at the risk level and at the technique level. This slide adds quantitative data now, properties, onto the same example chain to show how the ontology supports prioritization and trade-off analysis. The prompt injection LLM security risk is assigned a confidentiality impact score of 10. This indicates that if exploited, prompt injection in this financial aid context is considered maximum severity for confidentiality. Highly sensitive data could be exposed or misused in this case. The LLM security risk mitigation human oversight has an ease of implementation score of 4. This suggests that putting human review in the loop requires moderate effort, feasible but not trivial, involving processes, staffing, and workflow changes, for example. Then, the Atlas mitigation AI telemetry logging has an ease of implementation score of 2. This reflects that configuring logging and telemetry, at least in this context, is relatively hard compared to human oversight, perhaps because it demands engineering integration, storage, and monitoring infrastructure. By combining the class object structure with these data properties, the ontology supports questions such as, given a risk with confidentiality impact 10, what combination of mitigations gives the best reduction in risk relative to how hard they are to implement? This then lets organizations choose mitigation plans that are not only effective, but also practical under limited time and resources. WebProtégé is used to instantiate the abstract ontology with real-world individuals. In the individuals by class view, each class, such as LLM product, function, LLM security risk, or mitigation, contains a list of concrete instances like actual tools. For example, Microsoft Copilot or MapGPT as seen on the slide here. These specific prompt injection risks and name mitigations deployed in educational environments are also listed. Seeing these individuals organized under their classes makes it easy for security teams to trace actual assets and threats within their environment. Instead of thinking about LLM risk in the abstract context, they can see which precise products, functions, and risks are present in their K-12 setting and how they interconnect to one another. Going back a slide here, after defining the class hierarchy, the next step is to then populate the ontology with concrete individuals that represent real-world entities being managed. In the WebProtégé individuals by class view, as seen on the screen, each class, such as LLM product, function, LLM security risk, or LLM security risk mitigation, contains a list of specific instances that exist in the environment, like particular LLM tools, named risks, or concrete mitigations used by an organization. This transforms the ontology from an abstract schema into the living model of an actual LLM. For example, under the LLM product class, individuals might include tools such as Microsoft Copilot or MapGPT deployed in classrooms. While under LLM security risk, individuals might represent specific prompt injection or information disclosure risks that have been identified. Associating these individuals with the appropriate classes ensures that every product, function, risk, and mitigation is formally represented and can participate in queries, analyses, and reasoning. This step is essential for tying the ontology directly to the assets and threats that security teams are responsible for managing in practice. Data properties then in WebProtégé capture numeric or categorical attributes that enrich each individual with measurable characteristics. Examples relevant to this ontology include scores like function confidentiality impact score, LLM risk integrity impact score, and other CIA-related impact metrics. By standardizing these scores across the ontology, analysts can run quantitative comparisons rather than relying on subjective judgments alone. For instance, multiple risks can be ranked by confidentiality impact, or mitigations can be filtered by ease of implementation, enabling more systematic, data-driven security planning. The security risk ontology's complexity comes from its rich network of data properties overlaying the relationships among products, functions, risks, techniques, tactics, and mitigations. Each link can carry associated impact scores and other attributes for confidentiality, integrity, and availability, reflecting how a single vulnerability may propagate across multiple dimensions of risk. Instead of a binary view of safe versus unsafe, this structure captures nuanced, multi-layered effects of attacks and defenses. Analysts can assess, for example, how an atlas technique tied to an exfiltration tactic impacts confidentiality compared to integrity, and then select mitigations that best balance these competing concerns. This slide also talks about how, once fully populated, the security risk ontology becomes a complex, high-fidelity graph of the LLM environment. Each LLM product, function, risk, atlas technique, atlas tactic, and mitigation is represented as a node, and each object property, such as provides, impacts, exploits, achieves, or mitigates, is represented in a directed edge. Layered on top of this structure are data properties that assign confidentiality, integrity, and availability impact scores, as well as ease of implementation or other relevant metrics. That complexity is not just visual. It encodes the many-to-many relationships that exist in real-world cybersecurity today. A single LLM product may provide multiple functions, each exposed to several risks, which can be exploited by multiple techniques and countered by overlapping sets of mitigations. The ontology's richness captures this intertwined structure explicitly, which is exactly what enables advanced graph-based analyses. Instead of simplifying risk into isolated checklists, the model preserves these interdependencies so that security teams can better understand how attacks propagate, where defenses overlap, and where critical gaps remain. Now I will hand it off to Caroline to talk about our GPT model.
Now, let's discuss why putting the LLM security risk ontology into a GPT is important. In this image, you can see how easily accessible and readable our ontology is inside the GPT, where users can ask a variety of questions. Also, I wanted to add that this research is so important in K-12 schools as it protects personal data and private information involving financing. The GPT makes the model more accessible by giving users a clear structure to understand LLM security without needing deep expertise, meaning anyone can use this and understand complex topics by researchers. It acts as a dynamic training and education layer, adapting explanations to each user's skill level and helping teams learn continuously. It allows natural language questioning about the ontology, so users can explore risks, relationships, and mitigations simply by asking. It enables multiple algorithms to run over the ontology, supporting structured reasoning, automated classification, and impact analysis. It provides more precise and consistent outputs because the model is grounded in standardized concepts from the SRO. It improves the automation of security tasks, policies, and documentation, making workflow faster, more accurate, and easier to scale. And lastly, it future-proofs security by allowing quick updates as new risks and patterns emerge, keeping the model aligned with evolving threats. Here's a picture of how the GPT was created, further proving how anyone can take complex data and make it into an accessible resource for others. By providing a name, simple description, and instructors, as well as our ontology file and data, the GPT allows users to ask a diverse set of questions. Here are some basic questions that can be asked in our GPT. For instance, if you ask which atlas mitigations defend against the most techniques, the user will receive some defenses that protect against many attack methods, strong mitigations that block multiple attacker techniques, and these are most broadly useful safeguards. If you ask which atlas tactics have the most techniques pointing to them, the GPT will respond that some attackers' goals use many different methods, and state that tactics with many techniques are higher risk, and that these tactics show where the attackers focus their effort. Lastly, if asked for the exfiltration tactic, which techniques expose high confidentiality risks, the GPT provides techniques that steal sensitive data, methods targeting high-impact confidentiality weaknesses, and approaches that extract private or protected information. Let's look into the specific examples. With the first image, we can see that the GPT shows specific mitigations as well as how effective they are. We can see that the AI telemetry logging, which tracks AI behavior for attacks and detects many malicious actions, has a strong, broad security visibility and mitigates 6 different techniques. Restrict number of AI model queries mitigates 6 techniques, which limits attacker attempts, reduces the chances of repeated probing, and stops many trial and error attacks. Passive AI output obfuscation mitigates 3 techniques, which hides sensitive model details, prevents attackers learning system internals, and protects against system information revealing attacks. Generative AI guardrail mitigates 2 techniques, which blocks unsafe outputs, prevents harmful model responses, and helps stop prompt-based misuse. We asked the GPT to analyze Atlas ontology and determine which tactics have the highest number of techniques pointing to them via the chief's tactics relationship. According to the results, the tactics with the most techniques mapped to it is exfiltration using 5 techniques, with impact using 3 techniques, and execution using 2 techniques. These help us see which phases in the Atlas framework have the densest technique coverage, highlighting areas with greater detail or complexity. It also provides insights into how these specific techniques can help mitigate risks. We asked the GPT to analyze the Atlas ontology and identify which exfiltration-related techniques target LLM risks rated as high confidentiality impact. The GPT returned 3 exfiltration techniques that all map to the same high impact. LLM risk, LLM O2 information disclosure risk, shows that the techniques are inferred training data membership, invert AI model, and extract AI model. All 3 techniques attempt to expose sensitive model information, aligning them with the only exfiltration linked to LLM risk categorized as high confidentiality impact in the ontology. These prompts show how the SRO GPT can move beyond simple queries and perform real analytical reasoning in the Atlas ontology. The weighted greedy max coverage question helps us balance 2 things. 1, which mitigations are the most effective, and 2, which are the easiest to implement, giving us a practical, prioritized mitigation plan. The function-seeded personalized PageRank lets us identify which techniques are structurally most likely to be targeted as high confidentiality impact functions, essentially highlighting the highest risk attack paths. The smallest set mitigation question focuses on efficiency. What's the minimum number of mitigations that still covers the majority of weighted risk? This is especially great for constrained environments or resources. And the centrality analysis question surfaces the risks that matter most, those that influence large portions of the risk graph and therefore deserve priority and attention. A weighted greedy max coverage algorithm picks the most effective mitigations first by balancing how much risk they reduce and how easy they are to implement. The algorithm finds mitigations giving the biggest security benefit, but also factor into how easy each mitigation is. The results show that the best value mitigations for protection versus effort and that AI telemetry logging ranked highest overall, while generative AI guardrail was ranked second best choice. Personal PageRank PRR highlights which attack techniques are most likely to target specific high confidentiality functions by measuring their relative importance in the ontology. This means it shows the most likely attacks on sensitive functions. The GPT uses the ontology to rank techniques by the probability of being used and shows that direct prompt injection is highest risk, which helps prioritize defenses. Moreover, it demonstrates several techniques share a similarly high risk of likelihood of being attacked. In the example, the method of the ontology uses a smallest set mitigation plan, which finds the fewest mitigations that cover the largest amount of PRR-weighted attack risk, adding 1 mitigation at a time to maximize the total risk reduction. The results illustrate that 1 mitigation covers about 42% of the PRR risk, where PRR stands for potential risk reduction. AI telemetry logging is the best first choice, and 2 mitigations can cover about 61% of the risk. With guardrails added as the second most helpful, and that overall, more mitigations steadily increase total protection. Finally, in this instance, the GPT uses centrality analysis to identify which risks are most connected in the ontology graph, meaning they influence or are influenced by other elements. The GPT results show that prompt injection is the most centrally connected risk, unbounded consumption is tied for top critical risk, and information disclosure as well as misinformation risk are highly connected, and that central risks impact many parts of the system. Now, concluding it all up, what does this all mean? Ontologies can help evaluate the risk of organizational LLM usage by creating a shared vocabulary and clearly map relationships between variables.
An ontology-based GPT allows for various types of analyses, both basic and advanced, which provide insights about AI risk. By integrating our ontology into a GPT, the SRO GPT that Caroline just detailed, users can ask natural language questions that trigger graphs-based analyses. Basic analyses include questions such as, which atlas mitigations defend against the most techniques? Or, which tactics have the most techniques pointing to them? While advanced analyses use algorithms such as weighted greedy coverage, personalized page rank, and centrality to reveal most likely attack paths and high impact mitigation. Now I'll hand it over to, sorry. Future research includes adding more LLMs, expanding our ontology, focusing on integrity and availability, and examining domains beyond the K-12 educational landscape. Thank you.
So now I'm going to open the floor for any questions. And if you want, I can show you hands-on how we can use WebProtégé and show you our GPT kind of live if you'd like. But first, I'd like to see, are there any questions from the audience so far?
No. So when you guys are building the ontology, that tool, it seems like it's basically a relational database. Is that basically it? You guys built it by hand? Do you see any opportunity to build it with an LLM?
Yes. So yes, it's similar to a relational database, what's called a graph database. There's many-to-many relationships that can exist. That's why we use an ontology. It's similar to a knowledge graph. In terms of building it, yes. So we built it manually to make sure we had high fidelity of the data. But there are automated techniques to build ontologies. So for example, I know, just like Avery mentioned, like a lot of cybersecurity is done in spreadsheets. I know that was my experience down at the Philadelphia Navy Yard. Security is done on ships like spreadsheets. So there's ways to integrate the spreadsheets automatically into an ontology with some input tools. But yes, you can use the LLM to also create the ontology. So when there's like frameworks out there like the Atlas and OWASP, you can use like ChatGPT, like, hey, can you create an ontology for me? And for the GPT version, we're using the paid version. It's not just the free version. Yes, it's a excellent question.
And when creating the ontology manually in WebProtégé, I copy and pasted like each tactic or the technique used from the website, but I think the LLM can definitely be useful if you can just put the link in, maybe they can get all the information you need so it's more efficient.
Are there other questions before we show you WebProtégé and our GPT?
How are you all verifying that you're not getting hallucinations back from the LLM while you're injecting this graph database?
Yes, that's something we encountered when we first put the ontology into GPT. So we found one way to mitigate that was to give it clear instructions when we set it up. And also, we learned in our prompts, like, only use the data that's in the source ontology. Sometimes we have to remind it again and again, because, you know, AI, they think they're smart, but they're not always the smartest tool in the shed. But that's one way to mitigate it. But that's it. Excellent. We faced that before. Are there other questions about the ontology or the GPT? So I can quickly show you WebProtégé if you'd like. Our model's in there to show how easy it is to kind of create classes in there. I can show you that now. Okay. Should I use one of the physical mics? So as we discussed in the presentation, WebProtégé is an open source ontology editor. There's a version, a desktop version you can download a client. You can also use the web version, which is what we use to collaborate on this ontology data modeling project. So in WebProtégé, first you create a project, and in ontology modeling, the first thing you want to do is create classes, which are categories of objects. And what I love about ontology modeling, because I've done it, again, for the Navy, but I've published on it before, is that once you create kind of a core ontology, right away you see like, hey, there are other classes I can insert here. There are other connections I can make that are out there. And that's what I love about ontologies. It's like a flat database with many-to-many connections. And we can talk about other things we might add. So these are our main classes. If I want to add a new class, can anyone think of like another class that might add a category of objects? I have one in mind, but I can also think of another. So one thing in mind that we don't have here is we're really thinking about security risk of LLMs. Are the security settings of particular LLMs, such as allowing the data to be trained in the model? Can we limit the number of queries that are done each day? So I can easily add a, well, of course I have to log in. My password is 1234, don't use that. Just kidding. I hope. See work I do. Okay, so we have classes again. If I want to add another class, one class, about thinking about this project is we don't have anything in our model right now talking about specific security settings that one can select on an LLM, or an IT admin or cybersecurity admin may implement on an LLMs. So I can go here under things, how to model the whole world, and click on create. And now, of course, it won't let me. But hypothetically, I would be able to add a new class. Yeah, because I have it locked down. But it goes you to show like classes, also properties. Again, these are object properties where we can link two classes together. So we have like basic object properties here, but it's really easy to add in here. And with ontology modeling, what's great about it is like you work together, you as a team come up with how you want to label the data, how you want to label the relationships, and how it speaks to your domain. So what we use in the K-12 domain may be totally different than how you label things or describe things in your domain, whether it's private sector, the government sector. So we can use object properties for that. And also data properties are like attributes about particular objects. So again, it's easy to create new data properties or new data attributes. And for our scoring system, I forgot to mention that our scoring system is out of 10. So for example, like function confidentiality impact score, the score is out of 10. But again, in your teams, you can come up with whatever score and measures that you want. But adding the data properties with the numeric values allows you to do quantitative analysis over the ontology. And you can add many more data properties, and we also, of course, many more object properties. I start thinking of other things to link this to. I'm going to go back to classes. So of course, we can add security settings here. Perhaps you add people, like people in different roles. If you don't access role-based management, or actually particular names of people, because we have many different people that work at a K-12 school, including financial, accounting, facilities, security, students, teachers, nurses, and many more. So you can add them into the mix to analyze the risk of particular types of users. So after we create the ontology, it's always flexible, we can keep adding onto it. Then we can embed it into a GPT. Has anyone created a GPT before in ChatGPT? Yeah, it's really straightforward. We did it in our AI class, created different GPTs. But in the GPT, one of the things you can do is you have a source file, kind of like the main sources you want the GPT to reason over or calculate over. So that's where we downloaded our ontology from WebProtégé, and then we input that into ChatGPT and our own GPT. And from there, we can ask questions such as, if I'm working on this like we did as a team, if someone's new to this ontology, simple questions like, can you list the classes, object properties, data properties of the source ontology? And that goes where I had to say source ontology, so I wouldn't just kind of start making up stuff. And it lists the classes that are in there, and object properties, data properties, and then one can easily ask, hey, explain what Atlas tactic is or Atlas technique is. But from there, you can ask some of the questions that we asked in our presentation, like which Atlas mitigations defend against the most Atlas offensive techniques, state the full name of the mitigations. But one thing I love is the meta level. So the meta level is when the ontology is spelled out, as Avery was saying, with individuals, it becomes a knowledge graph. It knows specific entities in a domain. And what we can ask is, given the source ontologies focused on LLM risk and mitigations, what types of graph algorithms could be run over the source ontology? Describe each algorithm in 2 bullet points. So there's many different algorithms out there that are used to analyze graphs, such as like what is the most critical component in this particular type of graph? What is the shortest path from one node to another node in this graph? So many of these algorithms are really advanced, but now with the ontology in a GPT, you can find so many different types of advanced algorithms that will help us gain insights or look for patterns or help quantify the risk in our source ontology or in a domain that we're modeling. So many types of algorithms that are used. And again, this is relevant to the ontology modeling we did for the Navy. We created a graph of Navy ship systems, analyzed risk over there, and we used many similar types of algorithms to calculate the risk on the Navy ships. Now we're applying similar techniques with the GPT to analyze the risk on our K-12 system, our domain. Now I'd like to hand off now to you. Are there any questions or comments that you have about the research? All right. Well, thank you so much for attending our presentation. Round of applause for Avery and Brown. Researchers.